let's look at this exercise 1.1.5. So this exercise, basically this follows directly from the definition 1.1.2 of morphism chain complexes being quasi-isomorphism. It means that, still something to remark, I think. So quasi-isomorphism is not only saying that this is isomorphism, but it is saying that, following the exercise before, which tells you that if you have a morphism between chain complexes, it induces a morphism between homology module, which is mapping x bar to ux bar, if you remember construction before. And if this one being isomorphic, then we say this morphism is quasi-isomorphic. It could happen because a priori, to define this h and c dot and h and d dot, you don't really need this u. And if the isomorphism as a group, it doesn't mean it is induced by this u and you call this u quasi-isomorphic. It is the isomorphism induced from this u, which means exactly this map of morphism of homology group being isomorphic. Then we say this quasi-isomorphic. Okay, so solution: firstly, if C is exact, then by definition kernel dn quotient image dn plus 1 isomorphic to 0. This implies hn is 0, right, for any n. This implies 1 is 2. And so how about 2 implies 3? So there is obviously this map is a 0 map, which means u equals 0, and so it induces hn 0, still the 0 map to h and c. Is this 0 map isomorphism? It is, if we already know h and c is acyclic, because this is also 0, so which means mapping x to 0 bar, sorry, because x bar equals 0 bar, so 0 bar to 0 bar is isomorphism, 2 implies 3. In quasi-isomorphism, 3 implies 1. It's because once your quasi-isomorphism to 0 through this 0 map, then it tells you in particular of h and c at 0, and so it tells you that kernel equals image and so we are done.